Throughout calculus, we are going to be looking at working with a lot of different functions, and basically all of our functions that we are going to be working with are going to be built off of a core of some basic functions. So we can refer to these as the catalog of essential functions. So in general, when we use functions, we're talking about there's the reason that we are looking at them. A lot of times we have some sort of a real world problem that we are working on, and we model that real world problem with some sort of a mathematical formula. And a lot of times the mathematical formula is not perfect. It has a little bit of error, but it's sort of the best we can do to model it. We work with that mathematical formula and do math on it, and we draw mathematical conclusions, okay? And then we take those mathematical conclusions, interpret them back into the real world in order to make real world predictions. And a lot of times we will try to first test those predictions against what we've already observed to see if our model was a good model. And so we kind of go in this cyclic manner, and where sort of the bottom two pieces are looking at the real world piece, and then the top two pieces are looking at the modeled piece, the mathematical formulas. Okay, so I'm going to talk about the modeling process a little bit more in a different video, but I just want to go and look at the different the catalog of essential functions. And in each of these, it is important that you are aware of all of these different functions, these basic functions, and properties of them, how they increase or decrease, what their domain and range are, okay, and the symmetries or asymmetries of the functions. Okay. So linear functions are functions of the form ax plus b. If you graph a function like this, let's see, I'm going to graph something like negative 3/2 x plus 5. And so this is a linear function, and this particular function is a decreasing function. And you should be able to tell where in this formula you actually get the fact that this is a decreasing function. It comes from the negative slope. The slope is negative 3/2. That means if I take any one point on this graph, like for example this one, which is at 2, 2, I can find another point by going down 3 and to the right 2. Okay, or I can say to the right 2 and down 3. This basically says that y is decreasing 3 units for every increase of 2 units in x. That 5 is the y-intercept. We can think of that as a starting point. I'm going to make a whole video over linear functions because linear functions are actually so important. You might think that they are sort of beginner level functions, and that is true. But one of the things that we are doing in calculus is we are relating all of the more complex things to simpler things. And our most important model of a function that we will be relating everything to is linear functions. Okay. If you look at derivatives, derivatives are all about essentially pretending this function is a line. Okay. And I'll talk about that more later. Okay, polynomial functions, there's so many different polynomial functions, but you should know them as a sum of coefficients on powers of x, on positive integer powers of x. Okay, so here's an example. This is a 5th degree polynomial, okay? 5th degree because the highest power on any x is 5. And there's different properties of polynomials. They're a little bit hard to summarize, but you should have a lot of experience looking at polynomials. One of the things is you could see the degree of the polynomial tells something about the shape of the end behavior of the polynomial. So fifth degree odd degree polynomials have different end behavior on the right and left. On one side it goes up, and on the other side it goes down. This particular polynomial, it's fifth degree, and it goes up to the left and down to the right. The reason it goes up to the left and down to the right is because it has a negative leading coefficient. If it had a positive leading coefficient, then it would go up to the right and down to the left. If this was a fourth degree polynomial, then the end behavior, what I'm talking about with end behavior is the how the function behaves for large values of x in the positive and negative direction. So for an even degree polynomial, the end behavior is the same on both left and right. Okay, with a positive leading coefficient, it goes up on both left and right. And with a negative leading coefficient, and I'm gonna say that with a negative leading coefficient, the end behavior goes down on both left and right. There is so much more we can say about polynomial functions, but I'm not going to take the time to do that here. And I think this is a lot of the crux of what we need to know here. You should also know, like, that constant term here, what that constant term does. What does that constant term do in terms of the graph? See if you can answer that. I am going to move on. Power functions. So a power function is a function of the form y equals x to some power. So here, x to the a is 1 here. So this is the line y equals x. So I can look at y equals x squared, like that. There's y equals x squared. And I can change this to different integer values. And you should know what are the effects of positive integer powers of x? Okay, what are the properties? You might notice that all of these with positive integer powers have a domain of all real numbers, but their range is different depending on what? The range is different, and the end behaviors are different. You can also say the symmetry of the function is different. So these are positive integer powers. And you can look at what are some of the characteristics of these positive integer powers. But what if we did negative integer powers? That's interesting. Why is this the shape that it is? So there's -8, -7. So again, what is the domain and what is the range of these functions where the power, these are power functions with negative integer powers? What about if I used not integer powers, but fractional powers? Can I do this? Can I do 2/3? Okay, so there is a graph of a function where we have x to the 2/3 power. What does that mean? Can you remember what x to the 2/3 power means? Let me see if I can. x to the 2/3 power. Ugh. Okay. So what does x to the 2/3 power mean? Do you remember? So those fractional powers actually mean roots. So I think this particular program that I am using does not give me a way of writing cube roots, but I'm going to do this. This is the cube root of x squared. And I'm going to do this stupid thing of writing this. Okay, there we go. And it should be the cube root of x squared, not cubed. Okay, so that's what x to the 2/3 is cube root of x squared. Okay, so that tells you there's something happening here that is kind of, you see sort of a root picture. And you should be familiar with the 0.5. The 1/2 power is the square root. So this is a square root function. What is the domain of this? How do you know what the domain is? Okay, how would you know based on a decimal representation whether, like, what the domain is of a power function? So power functions, like, it's a little bit tricky to call this one category of function. It does exist as one category of functions for the sake of talking about differentiation. But for the sake of talking about properties of the function, it really breaks down into a lot of different things, because we have, positive integer powers have one behavior, which is very different from the negative integer powers. They have a different behavior, which is different from fractional powers. That's another behavior. Oop. And then negative fractional powers. Oh my goodness. Okay, and what if we had not fractional powers, but some irrational powers? So what if I put in a power of the square root of 3 or of pi? What is... can I write? Oh, there it is, pi. Okay, so it says 3.14, but it's actually using pi there. Like, what does it mean to have that fractional, that irrational power? So all of the power functions are going to behave in a certain way in terms of how we work with them in calculus, but the properties that they have as functions are very different. Okay. Rational functions are quotients of polynomials, okay? And there's a lot of different things about that we can say about the properties of rational functions. One of the things that you should be aware of is, how do you calculate the domain of a rational function? Okay, so polynomials, the domain is all real numbers. But when you divide, you have to restrict your domain. So you have to look at places where q of x is not equal to 0. Okay. So finding the actual places where q of x equals 0 involves oftentimes factoring, or maybe using some other powerful math, like using a quadratic formula or some other tools. But it's important that we have this awareness that our domain is restricted to any place where the denominator is not 0. Okay, an algebraic function, you may or may not have heard this before, but algebraic functions are any functions that can be constructed from polynomials using addition, subtraction, multiplication, division, or square roots, and not just square roots, any roots. So basically using rational powers. Okay, so algebraic functions, any functions that can be constructed starting with polynomials and adding polynomials, multiplying polynomials, dividing polynomials, taking polynomials to rational powers. Okay, and then combining, a polynomial to a rational power divided by a different polynomial to a rational power or times whatever. So here's an example of an algebraic function. And something that is not an algebraic function is called a transcendental function. Let me just write that. Okay. So if a function is not algebraic, it's called transcendental. This is not a super, super important word to know, but it's worth having in your vocabulary. The textbook we are using is called Early Transcendentals, which means that we are going to be dealing with the transcendental functions from the beginning rather than waiting till you've already developed your calculus tools and for all of the algebraic functions and then later applying them to transcendental functions. So what are the transcendental functions? What functions have we not talked about yet? You might see them down in the bottom here. Trigonometric functions are transcendental functions, exponential functions, and logarithms. Those are our basic transcendental functions. So the trigonometric functions, you should know how they are defined. You should know all of their domains and their ranges. And also the trigonometric functions are all periodic. So you should know what their periods are. If you need to review those, you might look, I forget, it's in, I believe it's in Appendix D in the book has trigonometry. But I think that you could also review this in section 1.2. But you could do this with exploration, pull out Desmos and graph each of these functions and remind yourself what's the period of tangent and what are the domain and the range. Okay. So exponential, very different from power functions. Power functions is x to the a. Exponential is a to the x. It is worth having an entire video on just exponential functions, but you should kind of know exponential functions swoop up if the base of the function, that's the a, if the base is positive, if the base is, so the base always has to be positive. If the base is greater than 1, then the exponential function swoops up. And let me see, can I do this? Okay, yeah, so the closer I get to 1, the seemingly flatter my exponential function gets. If I make the function equal to 1, this says my base, the base. If I make the base equal to 1, this is not an exponential function. This is a constant function. Why is that? That's because this function is 1 to the x. 1 to the x is always 1, no matter what x is. So making the base equal to 1, this is not an exponential function. It doesn't fit in that category. It is a constant function. So this is why we say the base can't be equal to 1. Okay, and if I make my base between 0 and 1, then my exponential function swoops down. It is a decreasing function. In both cases, and we could also see like what happens if I make the base negative, it is not defined. And that's worth thinking about. I'm not going to address this in this video about why the exponential function is not defined for a negative base. It's a very interesting question. If you want to talk about it, please come to my office hours and talk to me about it, and we can have a conversation about it. We could also talk about like what does it mean like when the base is equal to 0? Why do I have this like half line why don't I have a line over here? Something that you should be aware of, when you have a positive base that is not equal to 1, the domain of the exponential function is all real numbers, and the range, the y values used, are all real numbers greater than 0. Okay, they have to be positive. And if your base is between 0 and 1, then the function is a decreasing function. And if the base is greater than 1, then the exponential function is an increasing function. Okay. Logarithms are, logarithmic functions are inverses of exponential functions. And so you should see that there is a relationship between the shape of the exponential function and the shape of the logarithms. We will talk about this more when we talk about inverse functions. But you should know logarithms, the base, again, has to be positive and not equal to 1. And if the base is greater than 1, we have something going on. And if the base is less than 1, let's see what happens. Oh, if it's equal to 1, there's no function. If it's less than 1, you see this. So if the base is less than 1, we have a decreasing logarithmic function. If the base is greater than 1, we have an increasing logarithmic function. And the domain of the logarithm is all positive real numbers. The range is all real numbers. Okay, it's worth taking some time to like really cement a lot of these functions into your head. Properties of logarithms, you should know some properties of logarithms. And I believe that we are going to be actually reviewing those in section 1.5 as well. But you might want to review some properties of logarithms. There's some funny little properties there that you should remember. All right. I guess I don't know how to end videos, so I'm just going to stop right here.